Video. I hope you all had an awesome Halloween and it was super safe and super fun. What we're going to be talking about today is kinetics. So let's go ahead and jump right in. So most of the time that we're going to be talking about kinetics, we're going to be talking about proteins and ligands and how they bind, especially in biochemistry. So remember that this binding can happen with a non-covalent interaction between a protein and a small molecule, or also called a ligand. And these can be induced by hydrogen bonds, electrostatic interactions, hydrophobic interactions, or other things like that. Most of the time we're looking at the induced fit model for proteins. So it means that the binding site of the ligand isn't necessarily going to be the exact fit. It's going to have some conformational change, at least slightly, to be able to have the complex of protein and ligand together. Okay, so let's look at some of the equations that we've talked about in class. So most of the time we're looking at this equation of free protein and free ligand and it going to a protein ligand complex. That just means that it's a complex. And whenever we're looking at these type of equations, we're looking for our K value. And K, simply defined, is products over reactants. So in this case, our products are the PL complex, and then our reactants are the individual P and L. And remember that these are in concentration. That's very important. Okay, and then in this case, this is going to represent Ka because it provides the information for the association of our protein and our ligand together. So because we're looking at stuff going this way, we're looking at association. Okay, so one of the things that we can do with that Ka value is actually determine interaction strength. So interaction strength is the strength of the interaction that can be measured in terms of the binding free energy, or delta G naught bind, which is called the affinity. And delta G naught bind is equal to a negative RT ln of Ka. We can also use Kd, which we'll see in a second, but this is the equation for Ka. Remember that there is a negative there. That is super important. Okay, so what do we typically look at as biochemists? So we're looking typically at affinity in terms of equilibrium constant for the dissociation of ligand and proteins. This is just something that we've decided to do as biochemists. So typically we look at the reaction as complex and seeing how it falls apart because we care mostly about the dissociation. So for this, again, it's still products over reactants, but the position of products and reactants is flipped. So now our complex is in the denominator and our protein and ligand are in the numerator. So one thing to note is that Kd and Ka are just the inverse of each other, and because of that, when you're doing your delta G naught bind and you're using the Kd, then you're not going to have that negative up in front of your RT value, because if you remember, the natural log of 1 over Ka would be the same thing as bringing that negative forward, so it cancels out that negative. Okay, so let's think about Kd and what it actually tells us. So most commonly Kd is in units of molar, and one thing to note is as you go down in your molar amounts, so we go from millimolar down to picomolar, that means that you're going to get a stronger affinity. So a smaller Kd means higher affinity. So Kd is measured as the concentration of ligand required to bind 50% of the total protein concentration. So if you are titrating in your ligand and you have a certain amount of protein, whenever 50% of that protein is in complex with a ligand, that is going to be your Kd value. Okay, so some ways that we can actually determine Kd is the fractional saturation. So it has a max of 100%. Obviously, you can't go above 100% saturation, so just keep that in mind when we're setting up these type of graphs. You're always going to max out at 1 or 100%. So an experimental design that you can do for this is actually holding your P concentration constant, and you would titrate in the ligand and monitor the PL based on some fluorescence or whatever you're looking at. And that would actually help you in determining KD. So there's a couple different things that you can do with these types of graphs. You can do a scattered plot, which actually will give you a negative slope, and basically that gives you fractional saturation versus the concentration of your protein, and that'll provide you the KD from that. So there's a bunch of different things that you can do with that. We'll talk about those more coming up.